And if you just want to wait a couple of seconds, and then you're free to go.
Hi, I'm Xavier Jones, and I'm going to be talking about my project on dosimetric evaluation of a modulated intraoperative radiotherapy system, a measurement-based and Monte-Carlo modeling investigation. My supervisors are going to be Pejman, Marsha, and Gabor. And the contents of this presentation, I'm going to go through the background, talk about the aims, the methods, my project plan, the significance and benefits of the project, and some publications. Intraoperative radiotherapy is a specialized technique that combines surgery and radiotherapy. A high dose of radiation is delivered in a single fraction to a surgically exposed tumor bed, eliminating the remaining tumor cells. This provides improved local tumor control and reduces the need for radiotherapy post-surgery. It's usually used for breast cancer and also spine metastases and pancreatic cancer, among other things. The system that will be used in this project is the Carl Zeiss Intrabeam. This is a commercially available intraoperative radiotherapy system. It contains an X-ray source and a control console. The console provides the voltage to the X-ray source. The cathode gun within the X-ray source produces electrons to a max voltage of 50 kV. The electrons are accelerated towards a gold target and produces Bremsstrahlung X-rays, which are produced approximately isotropically, with a max energy of 50 kV and an average energy of approximately 20 kV. And this shows the X-ray tube here, and this is a close-up of here, which is the whole intravenous floor stand here. There's also an internal radiation monitor within the system here, which detects photons emitted back towards the cathode in order to record the dose output. The floor stand provides maneuverability to the X-ray source during surgery, and there are also applicators which fit over the top of the source here, the probe here. They modify the dose distribution. They come in spherical, surface, flat, and needle applicators. There's 8 spherical sizes from 1.5 to 5 centimeters in 0.5 centimeter increments. These are the applicators that are going to be mostly used in this experiment, among other things, which we'll get into later. The aims of this are to investigate modulated intraoperative radiotherapy techniques. I will be investigating applicator shield designs, such as material, thickness, shape, positioning of the shields, which will fit onto the top of the applicators. And I also investigate different applicator designs, such as different shapes, dimensionality, etc. This will be done through Monte-Carlo modeling, where I will be modeling the shields and the applicators and calculating dosimetric characteristics using the Monte-Carlo model, and also performing water phantom measurements of the models that I create through 3D printing of the shields and the applicators, and taking measurements using ionization chambers and film. For the methods, this project is an expansion of work by Marsha Chin. She performed a dosimetric evaluation of the bare probe and spherical applicators through Monte-Carlo and ionization chamber and film measurements, and similar methods will be employed in this study. So essentially, I'm going to start by reproducing Marsha's results in order to confirm her method and also to improve my understanding of the method so that I know for later use. But I'm going to start by calibrating the film that I'm going to use using a superficial X-ray machine, which wasn't done by Chin. So Chin, she modeled the Monte-Carlo in 2 steps. She first modeled the bare probe, used that to generate a phase space file, and then using the phase space file, she modeled the spherical applicators. The bare probe was modeled using an electron source with a Gaussian energy distribution of 50 keV mean, 5 keV full width half maximum. The electron beam was modeled as 2 rings with radii 0.6 to 0.7 and 0.7 to 0.8 millimeters, which is based on literature. The material and composition of the probe is shown in this table here. The body was produced of mu metal, and the end had a beryllium window. The target was gold with thickness of 1 micrometer, and there were biocompatible coatings of nickel oxide, nickel, chromium nitride on the edge of the probe. This is important because some papers didn't use all of these, which would result in slightly different results. Here's just an example of the phase file that was used of the bare probe. And then from there, 8 spherical applicators were modeled. These were composed of polyethylamide. For applicator diameters of less than 3 centimeters. There was a layer of aluminium included, which provided beam hardening. Here's a picture of the models and the materials used. This is a 2.5 centimeter applicator, so it has the layer of aluminium. Yeah. They were modeled in a water phantom. All simulations have 10 to the 9 histories, and percentage jet dose and isodose curves were extracted. And here's just some of the code for the geometry of the applicator. The results were compared and measurements were compared to measurements made in the water phantom for the bare probe and the applicators. Percentage depth dose curves were produced using ionization chamber measurements using a PTW 34013 soft X-ray parallel plate ionization chamber. Ionization isodose curves were also produced by film. Gap chromic EB33 film was laser cut. For a bare probe, the central circle was cut out, and doses of this at 10 milliliters from the probe center were irradiated in the water tank. For the purpose of my project, I might leave this out for the purpose of time because it isn't completely relevant, but we'll see. And then the applicators, for measuring the applicators, a semicircle was cut into one edge of the film, and each applicator was irradiated with 2 grays from the 10 millimeter from the surface. This shows the setup here of the applicator being irradiated in the water phantom. For the purpose of my project, I might, instead of using a semicircle, I will use a whole film sort of surrounding the applicator, which I'll go into later why. But if that happens, I might need to recreate a film holder, which is pictured here, and possibly use a bigger phantom because it might not be big enough to get enough information from this size. So in my work, I'm going to compare Monte-Carlo and the measurement results and that I get and compare them with Chin's results. And then using Chin's Monte-Carlo code I will model the applicator shields. So I will simulate the effect of different materials and thicknesses of the shield, and also the effects of size, positioning of the shield, and extract dose distribution information. This is an image of what I mean by applicator shield. The shield will be directly on the applicator. And then I will 3D print the shields, likely using tungsten, because I believe that's the only thing available to 3D print the only metal. So even if I find a different material was better, I'd likely have to use tungsten. And then for water phantom measurements, I'll do similar methods as I've already described, but because of the loss of isotropy because of using these shields, this is why we'll have to use the film cut centrally instead of a semicircle on the edge. And there's also the possibility of using different orientations of film. Instead of just on one plane, I can do different planes because of, again, the loss of isotropy. There might be more information that you can find by taking different planes. And then I'll compare these Monte-Carlo results to the measurements I take in the water phantom, and also to the results from the unshielded applicators in order to find the difference. And then for the third part of this, I'll use Monte-Carlo code to model different applicator shapes, such as ellipsoids, different dimensions, possibly other shapes, and extract dose distribution information and use that to determine the effects of different shapes and dimensions on the dose distribution. And then these will be 3D printed using polyethylamide. The 3D printed applicators will be CT scanned in order to ensure that they have the correct shape and the homogeneity of the material is correct. A possible problem is that for applicators with diameters less than or equal to 3 centimeters, there's the aluminium layer, which if I want to compare the applicators of similar dimensions, the aluminium might be a problem because of 3D printing might not be able to do that. Possible solutions might be using aluminium foil. Not sure yet. That's more investigations needed here. And yeah, again, same water fountain measurements as before, but due to the loss of isotropy, the same things I mentioned before with the film. The hole in the center, possibly different orientations. And then again, I'll compare the results with the spherical applicators of similar dimensions that I found before. This is just a flowchart of the project plan. Here's the starting part where I reproduce Marsh's results. Here's just the shield investigation, and here's the applicator investigation, and they'll all be compared with this one here. The significance benefits. This will provide improved understanding of modulated intraoperative radiotherapy techniques. It will lead to improvements in dose conformity during intraoperative radiotherapy, leading to increased tumor control and reduced normal tissue complication due to less dose to normal tissues due to the increased conformity. This may lead to patient-specific intraoperative radiotherapy techniques where different applicators shields designed for the specific patient that's being used on. And the results from this may be used in treatment planning system development. And there's a possibility, if time and my own personal skills allow, I could attempt to use this information to produce a treatment planning system. Here's just a summary of some of the publications. Here's Marsha's publication. Here's some of the results from Marsha's paper. Is the Monte-Carlo simulated isodose curves. Here's some of the film irradiation, and here's the isodose curves extracted from this film here. Thank you. Are there any questions?
Great, thanks for that, Xavier. Fantastic presentation. Are there any questions for Xavier? Martin?
Thanks, Xavier. Thanks for that. Just a couple of questions. So you mentioned when you're looking at the shielding, you mentioned you might find a material that's better than tungsten that you can print in. How do you define what's better? Like what's going to make one material better than another one?
Well, a half value layer, probably. Well, we just have to. What's better? Well, if we need something that might be better, but because it is really thick and clunky, it's not going to be actually useful in the intraoperative radiotherapy, like during surgery, then that's not going to be a better, I don't think. But yeah, it kind of depends.
Just another question. So the applicators, as they come standard, are spherical, which is a sort of a useful shape when you're putting it into a resection cavity because it tends to be a spherical cavity. So one option is, I guess, to use the shield, a non-uniform shield. The other one you mentioned is printing an applicator with a different shape to get the modulation. Do you think another option might be to print it as a sphere, but using different density materials?
I was also thinking about that. Yeah, you can use different densities in order to modulate it. That's another thing that can be done. Might think about doing that as well. Yeah.
Thanks.
Thank you.
I have just one question. Usually in KV energy range, when they, of course, it's usually they're using the device, and when they're using like a LED cutout to collimate the beam further, and they usually cover it with some either some paint lacquer or some low Z material to reduce the electron contamination to the surface dose. So in this case, maybe you don't have to wrap it in aluminum, but maybe just use some kind of coating, and you can find out, you know. And I'm not sure, because in our case, if you do the measurements, of course it will be in a water submerged, not at the surface, but still we have to investigate that effect. But it will be a little bit later down the project. But we have to find something to coat your 3D printed one. So I think maybe the paint or this lacquer will be the best solution, but we have to find out, because you try to cover it with aluminum foil, it's not the best. Yeah, worth a try, simulate it.
Yeah.
But yeah, you have to find some better solutions.
Thank you.
Asha, did you want to jump in?
Yes, please. Thanks so much for that presentation, Xavier. I just have one question. Do you know how often the shields are currently used clinically for each patient?
I don't actually know. I couldn't really, there wasn't much information in the literature on the shields I could find, so I don't particularly know how often the shields are actually used.
That's okay. Maybe Gabor might know.
Godfrey, did you want to jump in? You got a question?
Yeah, shields are used by other centers. Here we never really use them, but other centers use them. And I guess it depends on case per case. My comment really is on how you want to do your measurement. I just wanted to say that the energy you're dealing with is very low, and there's very high uncertainty when you position a detector. For that comparison with Monte-Carlo, it's something that you need to think through as you kind of work out, those shields and how you do the actual measurement. Otherwise, that might not correlate, or might correlate because of by just coincidence. The measurement is going to be a bit tricky.
Okay.
Because of the high uncertainty in those low energy.
Okay.
Something to think about. Yeah.
Something to think about. Yeah. Thank you.
And I think we'll have time for one more. Luke, if you wanted to jump in with your question.
Yeah, I had a quick question. You mentioned potential for making patient-specific applicators. Do you see any issues with that? Because generally when they go down to treatment, they cut the tumor out and then they basically try to fit an applicator that matches the tumor bed. So do you see, if you make a patient-specific applicator, do you have to print 5 different sizes or something before the patient goes down, or how do you see that working?
Well, yeah, it'll have to be something to do with some sort of imaging in order to try and guess like what the approximate size of the tumor bed will look like, and try and 3D print out something out that would resemble what the tumor bed would look like. It would be costly in order to do this for every patient, and yeah, there is a possibility that we might have to 3D print out a few more. So yeah, but it might still be better than just using the spherical applicator for everyone.
Thank you.
Great, thanks for that, Xavier. Great presentation. We're going to have to leave it there so we can stick to the time. So if you want to stop sharing your screen, Xavier, I'll stop this recording.